but the link that I shared to everyone is now not working. So that's taking a little.
Who's that?
It's just YouTube.
YouTube. Okay. All right. So, welcome to the PhD defense of Robert Hedrick, or Robbie, as you call him. One said the other part of the nickname. At the University of Oklahoma, where he studied chemical engineering, and then he decided that chemical engineering was boring and he wanted to do chemistry. So he started where he's pretending to be chemistry, because this is a very welcoming community, with a broad view of chemistry. Hopefully, the community will consider this as legitimate chemistry. So, well, if they let me be chair until now, probably they can take this. So, I see that this is almost like a match defense, so with the people for the candidate on one side and against the other. For those who haven't been to a defense here right before, Robbie will give a talk for about 45 minutes to an hour. We can ask questions and make comments during the talk, and then the audience and the committee can ask questions. And then we'll ask the audience to be excused, and we may ask further questions to Robbie, and then Robbie will be excused, and the committee will deliberate. As part of the committee are Professor Jim Connell, as Professor of Electrical Engineering and Physics, and Professor Del Marti, a Professor of Chemistry and Material Science and Engineering, and I'm Matteo Pasquale, Professor of Chemical Engineering, Chemistry, and Material Science and Engineering. Say enough?
Yep. Great, thank you, Matteo, for the introduction. Thanks everyone for being here. I'm really excited to share with you the work that I've been doing at Rice during my PhD over the past 6 years. As you can see, my title is really long, so I've been told multiple times. So I'm not going to read it to you, but go ahead and jump right in. So I'm going to start by introducing sort of the star of the show, this carbon nanotube material. So carbon nanotube is a class of material composed entirely of carbon atoms. The carbon atoms are sp2 hybridized and arranged in 6-member rings. And you can imagine a single wall carbon nanotube as a graphene sheet that's been rolled up into a seamless cylinder. So this hollow tube, high aspect ratios. You can also have multi-walled carbon nanotubes, which would consist of multiple concentric single wall carbon nanotubes. Now, carbon nanotubes are a really interesting material from a research perspective because at the molecular level, they have really phenomenal physical properties, which includes a very high tensile strength. They can have high electrical and thermal conductivities, and these are coupled with very low. Using carbon nanotubes in the future for advanced material applications, such as improving energy generation and electrical transport, flexible electronics, body armor, improvements in the aerospace industry, and perhaps someday an elevator to space. Now, to get carbon nanotubes into these applications, one of the most scalable methods is through solution processing. And here I'm showing two generalizations of some of the most used, most widely adapted methods for processing carbon nanotubes in liquids. So you can tip sonicate carbon nanotubes to get them individualized into an organic solvent or in water using a surfactant. Or you could covalently functionalize carbon nanotubes. So you perform some surface chemistry to render them soluble in an organic solvent or in water. However, both of these processes deteriorate, or they're destructive to the individual carbon nanotubes, which deteriorates the really interesting properties that made carbon nanotubes interesting in the first place, which translates directly to poor macroscopic properties when you assemble them into a large material. Alternatively, carbon nanotubes will spontaneously dissolve into superacids, which means you can just mix them together and they'll dissolve into the acid and individualize as if you're dissolving sugar into water. One of the main acids that we use in our lab is chlorosulfonic acid. So this is a clear superacid solvent. And you can tell by this cryo-CEM image that the nanotubes are individualized in the acid. Now, this dissolution mechanism relies on direct interaction between the acid solvent and the carbon nanotube surface. So the acid will protonate the surface of the carbon nanotube and cause a partial positive charge to delocalize along its length. As more and more nanotubes in a bundle become positively charged, adjacent nanotubes are now repulsive, and the nanotubes can be individualized and moved into solution. Now, when nanotubes are in solution, they actually behave as rigid rods. And what this means is that at low concentration, the nanotubes are randomly oriented in space, and they form this isotropic phase, as you can see by this cryo-CEM image. If you take that sample and you place it between cross-polarizer and analyzer and look at that sample under a microscope, the image is just dark because none of the light can pass through the sample. However, if you start to increase the concentration of the nanotubes in solution, eventually a fraction of the nanotubes will spontaneously align into nematic domains. So this is the formation of a liquid crystalline phase. This phase will coexist with an isotropic phase, so this is a biphasic system. And if you place that sample between cross-polarizer of the liquid crystal. If you continue to increase the concentration of the nanotubes in solution, eventually all of the nanotubes transition into a liquid crystal phase, and you have a very bright birefringent sample under cross-polarizer and analyzer. So solution processing with chlorosulfonic acid is a really strong and powerful tool that we use in our lab quite often to take carbon nanotubes from a manufacturer where they're sort of this disorganized and useless state and transform them into more functional morphologies, such as thin transparent films, one-dimensional fibers, and even three-dimensional porous foams. So the research objectives of my PhD, in a concise statement, would be to study the inherent CNT properties and manufacturing shortcomings that have limited macroscopic material performance and application. And so to go along with my really long title, I have a lot of bullet points that are covered in my thesis. But in the interest of time, I'm just going to focus on 3 areas. So first, to tell you about a method that I've developed to solution process nanotubes into aligned films, and then how we can take those films and turn them into carbon nanotube fibers to study the structure property relationships. And then I'll tell you about a method I've developed to characterize carbon nanotube fiber linear density bioscopically. And then I'll introduce, in the third and final part, some new non-corrosive acid solvents that we've developed for processing carbon nanotubes into high-performance materials. So the first section is structure property relations in carbon nanotube fibers by downscaling solution processing. So I'll start this section by just giving you an overview of how we produce carbon nanotube fibers through a solution spinning method. So our lab has been publishing on this since 2004 using superacid solvents. And this continuous solution spinning method in general starts by just taking nanotubes and dissolving them into a superacid such as chlorosulfonic acid. You can take that solution and then filter out any large particles, and then put it into a syringe pump to extrude that fluid through a really small hole or a spinneret. So you're extruding this fluid directly into a coagulant bath. This coagulant bath is going to remove the acid solvent, causing the nanotubes to precipitate into an aligned fiber structure. And then that fiber can be continuously collected on a winding drum. Now, if you take a closer look at the scale of the solution spinning aspect of this procedure, we can see that typically you need at least, at minimum, 5 milliliters of acid. And usually you work with around 2 weight % carbon nanotubes in solution. And this translates to a material requirement of 175 milligrams. Additionally, you have about half a milliliter of dead volume inside the spinneret, so you're wasting each experiment a large fraction of your nanotube sample. Now, in most material science cases, 175 milligrams is a really tiny amount of mass. But in the carbon nanotube world, this is a massive quantity of nanotubes, and this can be really problematic if you're trying to study the properties or trying to spin fiber out of more exotic carbon nanotube samples, such as those enriched in chirality or metallicity, which are only available in the 1 or sub-milligram scale. Additionally, each solution spinning experiment takes about 2 days, and if you get a batch of nanotubes from a manufacturer, it takes multiple experiments to find the optimized processing parameters before you can produce the most high-performance carbon nanotube fibers with that particular material. So for this reason, we needed a method to downscale our ability to process nanotubes into fibers so that we could work with smaller quantities of nanotubes And we wanted to be able to speed things up so that we could characterize the properties of nanotube fibers with different batches. That I've developed to address this actually begins by producing an aligned thin film. So we take solutions of carbon nanotubes with fluorosphonic acid. We sandwich that fluid between two glass microscope slides. We can place that sandwich into a Teflon sliding guide, which allows us to shear the two glass slides apart. The shear force causes the nanotubes to align in the fluid phase. And then the glass slides are deposited into a coagulant bath, which removes the acid solvent, causing the nanotubes to precipitate onto the glass surface. So the product that you get out of this process is two glass microscope slides with aligned films of carbon nanotubes on their surfaces. So we can start to characterize the morphology of these films by looking at high resolution SEM. So in this case, the shear direction is from top left to bottom right. You can see the nanotubes are oriented in aligned super ropes in the shear direction. And if you zoom in, you can see that there's a small quantity of tiny bundles of nanotubes that are oriented perpendicular. Look at the anisotropic optical properties of the thin films. So in this case, we're taking a thin film and placing it between aligned polarizer and analyzer and rotating the stage. So the carbon nanotubes will preferentially absorb light that is polarized parallel to their length. So you can see as you rotate the stage, the absorbance is changing. We can plot this absorbance changing with angle and get these curves here that fit a sine squared equation. And with this data, we can calculate a dichroic ratio, and for this film, we get a value of 3.3. We can do a similar experiment with crossed polarizer and analyzer to look at the birefringence of the thin film. You can see we get this nice pi/2 periodicity and intensity, which fits a cosine squared sine squared relation. So we can start to quantify the quality of the alignment using polarized Raman spectroscopy. So in this experiment, we're going to take Raman spectra in the G-peak region of the nanotubes with 3 different polarization geometries. We'll take the intensity of the G-peak at these 3 different scattering geometries and plug those values into these equations. These equations will allow us to calculate an order parameter, which is just a number that varies from 0 to 1, 0 being fully isotropic and randomly oriented, 1 being a fully aligned thin film. And the only difference between these 2 equations is that the bottom one takes into account anisotropic absorbance of incident and scattered light. And the top equation, and it's doing that with the dichroic ratio. And so the top equation has the dichroic ratio set to equal 1. And so you can see for the film that we've been analyzing, we get an order parameter of 0.47. And if you take into account the dichroic ratio, that number gets bumped up to 0.73. So the nice thing about Raman spectroscopy is that you can create relatively large scale maps quickly. And so this is a 10 by 3 millimeter map of an aligned film. And the order parameter is calculated in 900 different positions. And you can see on average, we get a value of 0.73. So this tells us that the alignment is relatively homogeneous across the surface of the film. In fact, the alignment is consistent across the entire 7 centimeter length and 2.5 centimeter width. This one of those thin strips and hand twist it into a nice cylindrical carbon nanotube fiber. And it turns out that these fibers have really high tensile strength. So here I'm plotting stress strain curves for 5 carbon nanotube fibers peeled from a single film, and you can see on average they have a tensile strength above 2.5 gigapascal. So from a single film, we can peel 10 or more fibers. Each one is about 7 centimeters long. So this is really awesome. This allows us now to produce carbon nanotube fibers at the sub-milligram scale, whereas with the full-scale solution spinning method, you needed 175 milligrams. So we've reduced the mass requirements by quite a lot. Now at this point, it's not clear how we optimize our fibers or what processing parameters optimize the fiber properties through this method. So to investigate that, we're going to look at the dependence of the fiber tensile strength on the thickness of the film that you produce. So here I'm plotting the tensile strength for multiple fibers peeled from 5 different films, ranging in thickness from 1.7 micron to 0.4 micron. And the nominal tensile strength for fibers produced through these different films increases from 1.5 gigapascal all the way to 2.8 gigapascal as you decrease the film thickness. So what this tells us is that the optimized or the highest tensile strength we can achieve is actually by using a thinner film. So we can start to try to understand this by looking at the actual fibers themselves. So we cut them with a focused ion beam and look at their cross-section. And you can see immediately that the weaker fiber has a crack that propagates radially through the cross-section, whereas the stronger fiber, prepared from the thin film, has very little structure or porosity that's visible at this scale. If we zoom in, you can actually see remnants of the scrolled film that measure in thickness of about 1.7 micron, which is the thickness of the film. So you can see that there's very poor interlayer bonding within this cross-section of this fiber that's reducing interlayer stress transfer and reducing the tensile strength. In the zoomed-in image of the stronger fiber, the only pores that are visible are on the order of 100 nanometers. So there's a dramatic difference in the internal packing density in the cross-section of these fibers that's resulting in the improved tensile strength. And we can look, we can take a non-destructive look with X-ray computed tomography. In this case, we're using phase contrast imaging. So phase contrast imaging is going to highlight differences, interfaces within the fiber or differences in density. So essentially, all of the contrast you see in these, all the contrast you see in these images is basically porosity within the fiber structure. And so you can see, again, the dramatic difference between the internal packing density between the two fibers that is directly resulting in the improved tensile strength.
So do you know the packing density?
No, so one of the issues with this is that I'm choosing the thresholding for the imaging processing. So I tried to set them to be equivalent, but I'm not sure how to go from that to calculating porosity or something like that. So from this, we learned that sort of the optimal processing method for producing high strength carbon 2 fibers with this of 400 nanometers. So you might be wondering now, how do these fibers compare to our full-scale solution spinning method? So here I'm applying the tensile strength versus electrical conductivity. The carbon 2 fibers prepared by this method and our solution spinning method. And you can see that the tensile strength for twisted films is higher than what we get for the solution spun method. So this is many different batches of carbon nanotubes. However, you can see that the electrical conductivity is actually pretty similar between the two methods. So of course, we can look with X-ray computed tomography to see differences in the internal structure. And you can see that the solution spun fiber has almost a little bit of a dot bone structure, and it's got a crack that moves to the center, and an increased contrast in the center, indicating that there is a porosity within this fiber relative to the stronger twisted film fiber. And this is likely resulting in the increased tensile strength for the twisted films. Interestingly, if we characterize the quality of the alignment with this order parameter based on polarized Raman spectroscopy, we see that the alignment in all of the solution spun fibers is higher than what we get with our shear aligned films. So what this indicates is that above a certain degree of alignment, tensile strength in our fibers is actually more dependent on internal packing. So this is important because this gives us a path forward for improving our ability to spin carbon 2 fibers, where we can now start to try to optimize processing parameters that increase the internal packing density, and perhaps that will lead to an improved single wall from Comocat. There's some double wall from Unidyne in the solution spun. There's a few EDIP samples that are not made by Majo in the data set. Right, so I would say 4 of these batches, I think, are the same between the 2 experiments, and then there are a few that are not produced by both methods. So now that we have the ability to produce optimized carbon 2 fibers relatively quickly, you can start to characterize how the characteristics of the constituent carbon nanotubes impact the fiber properties. So here we're looking at the tensile strength of carbon 2 fibers versus the aspect ratio of the constituent nanotubes in the fiber. And you can see that the tensile strength scales with CT aspect ratio, following a power law with a slope of 1.2. So this is really important when we look at how our material compares to what's out there in the literature. So here I'm plotting the tensile strength versus electrical conductivity of the fibers we produce with superacids relative to the solid state processing with CVD and array, and what you can find for multifunctional carbon fiber. And you can see that our electrical conductivity is higher than these other materials, and our tensile strength is now on par with CVD and carbon fiber. So the goal of our work is essentially to keep pushing to the top right of this corner corner so we can surpass the properties of the materials available and achieve the highest performance carbon nanotube fibers possible. And the way that we can do that is by one, increasing the internal packing density of the fibers. And this data tells us that as we continue to get our hands on higher quality and higher aspect ratio nanotubes, we can also expect our tensile strength to continue to increase. So that's the end of this section. I'll just conclude by reminding you, we prepared highly aligned thin films of carbon nanotubes, which could then be transformed into high performance carbon nanotube fibers, which allow us to study the structure property relationships. And this fiber production process is at a scale that's 3 orders of magnitude lower than previously required. We've also reduced the experimental time required for producing high performance carbon nanotube fibers from multiple days down to about 1 hour.
So Robbie, just to see if I understand, so with this technique you can get fibers that are stronger than with spinning, that's what you're saying?
Yeah, quite a bit stronger, using the exact same carbon nanotubes.
But it's typically packed better.
Right, it's because our data suggests it's because it's much more dense.
And
yeah, that was actually a question that would follow that.
It's a little unclear, but one thing I can say is that we sort of associate the spread in this data to differences in and the weakest fibers in these data sets are stronger than what we have with solution spun. So I can say that it's not necessarily true that twist is the culprit in terms of what's increasing the tensile strength. The effect of twist, I think, is actually kind of small. I don't. Okay, so now I'll move on to the second section of my talk, where I'll tell you about a method that we developed for measuring carbon nanotube fiber linear density microscopically. So I'll start with a quick point of motivation. A lot of material applications in performance are limited by weight requirements, particularly in the aerospace industry. For example, the space shuttle program cost NASA $10,000 to put 1 pound of mass into space. Similarly, a Boeing 747 has 4,000 pounds of copper wiring on board. So obviously, weight reduction in this area is very valuable. And so the density of different materials is something that must be considered when you're speccing them for these types of applications. Of course, carbon nanotubes have the potential of offering a lightweight alternative in terms of high strength and high electrical conductivity materials. And therefore, it's really important that we characterize properties of our fibers by normalizing them by their density. So here I'm showing a plot from a paper out of our lab in 2013 that shows the tensile strength and electrical conductivity normalized by the density for the fibers we were producing at that time relative to metals and carbon fibers. So you can see that our data is starting to push into this top right quadrant. And again, that's sort of the goal of our research, is to continue pushing to the top right so that we can outperform carbon fiber and metals on a per mass basis. So you typically make this characterization by measuring the linear density, which comes in a unit of a tech, which is a mass per unit length, or a gram per kilometer. And you would do this with a carbon nanotube fiber by taking a known length and then measuring the mass on a microbalance. However, this is not possible to do when you're working with a 7 centimeter long fiber that's 20 microns in diameter, like the ones we just talked about. The mass of those fibers is too low to be detected by a microbalance. So to characterize the specific properties of those materials, we have to come up with a new method. And the method that we have developed comes from Marcin's laws, which says that the resonant vibrational frequency of a suspended filament depends on its length, the tension that it's under, and its linear density. So this is essentially the equation that governs the sound that's produced by a vibrating guitar string. So with a carbon nanotube fiber, if we take a suspended carbon nanotube fiber and we know the length, and we measure the tension on it, and we cause it to vibrate at a known frequency, then we can back calculate the linear density. And so the way that we accomplish this is by taking the fiber and suspending it over a permanent magnet. On one end, we have a motor so that we can pull on the fiber. And on the other end, we have a load cell so we can measure the tension that's on the fiber. We then send an alternating current through the fiber at many different frequencies. And as we pull on the fiber, Eventually, it will come into resonance, dependent on this equation, and it will start to vibrate due to the presence of the permanent magnetic field. The vibration of the carbon-82 fiber produces a sound that we can record with a microphone. So we take that sound, we analyze the frequencies, we know the length because we chose that, we measure the tension with the load cell, and now we can back calculate the linear density. So this is an example data set. On the top, I'm showing the spectrogram of the sound that's produced by the vibrating carbon-82 fiber. The y-axis is the frequency of the sound, and the x-axis is time as we're pulling on it. The bottom is the tension on the fiber as we're pulling on it. So you can see as you increase in tension over time, the frequency also increases. So you can just choose a frequency, find the corresponding tension. We know the length, plug these values into the equation, and then you can calculate the linear density of that fiber. So we've done this.
So Robbie, each one of those data points gives you a linear density, right?
Yep.
How much does it change over that experiment? Actually,
So we've done this experiment with 5 different fibers. So I'm plotting the linear density versus the frequency that you choose. And the carbon-82 fibers span in linear density from 0.77 decitec all the way to 12 decitec with the heaviest fiber. The horizontal line is the value that we measure with the microbalance. The width of that line is about 5% error, which is typically what we get with the microbalance. And so you can see we're able to accurately characterize the linear density of the fibers at higher frequencies. But at lower frequencies, you can see some of the data starts to trail off. It's not totally clear what's causing that at this point in time. But I will say that these experiments were performed in a loud room, and the sound of the carbon-82 vibrating is really quiet. So that's definitely something that we can fix as we move forward with these experiments. Additionally, the tension is quite slow. The experiment where we're pulling on it is done really slowly. And I'm worried that the fiber could slip a little bit, or there could be some creep in the fiber that's going to also add some errors to the measurements. So we're working on improving our experimental setup to try to accommodate and take each of these factors into account so we can remove this error.
was this done at NASA or here?
This is done at NASA.
And so it was noisy there too.
It's really noisy in that room, and there's jets outside, and the motor clicks, and there's a lot of data processing to get it to look like that.
What about in our case? It's in the acid lab, right?
It's in the acid lab, but I guess Mitch moved it. But we can even put a little foam around it to.
Where is it now?
It's right next to that 3D printer. Right.
Feel that stretch.
That's
So
an option.
then we can close the door. Anyway, go ahead.
Can you hear the noise?
Yeah, you can hear it. You know, sometimes you can see a vertical line of the sound of it breaking, but you can hear it at least in the file. You can't hear the break in real life very well, but you can hear it in the file.
So what note is it?
It's a lot. It's a vertical line in this plot. So
No, but what notes are they? Like if somebody were playing guitar
Oh,
or
I
whatever, like
I have no idea.
the solo, the metal, like really, I mean, that's pretty high for some.
Yeah, these are.
But it's still audible, so.
But they're, if you were doing much heavier nanotubes.
Right, then it would be more like a bass guitar.
Yeah.
Sure.
Okay, so the last thing I want to point out about this is that although it does seem to work, it's very sensitive to the gauge length that you set. So if you're off by 0.5 millimeter in the length, that results in about 5% error. And 0.5 millimeter is actually really hard to control experimentally. So that's definitely something that has to be considered as we continue to analyze data with this method. So that's the end of this part. In conclusion, we were able to accurately characterize carbon-82 fiber linear density fibroscopically. We did this on fibers that spanned linear density by an order of magnitude. However, like I said, it's very sensitive to the length measurement, and we should probably try to figure out a way to make that a simpler method for getting the gauge length accurately. So now I'll move on to the third and final section, where I will tell you about some versatile acid solvents that we've developed for processing carbon nanotubes. So to revisit one of the first slides I showed you, I mentioned that these common fluid processing methods lead to poor macroscopic properties, and so you may have been wondering, then why would anyone use these methods? Well, one major reason is because aqueous and organic solvents are very convenient for drop-in printing and coating applications. You can imagine if you have carbon nanotubes dispersed into water, you could very easily if you're going to do this with a superacid such as fluorosulfonic acid, this would completely destroy your inkjet printer. So there's this big disconnect between these two processing worlds. Where on one hand, with superacids, you get excellent material properties, but the acid has poor chemical compatibility. On the other hand, aqueous and organic processing has excellent chemical compatibility, but you get very poor properties. So we really want to be able to bridge this gap and get the best of both worlds. So the way we can start trying to go about doing that is begin by taking a closer look at understanding the strength of the interaction between the acid and the nanotube. So I told you in the beginning, the dissolution mechanism relies on direct interaction between the acid molecules and the carbon nanotube surface. So this protonation process actually causes the carbon-carbon bond stiffness to increase, and we can probe which have a diameter of about 1 nanometer. And the bottom spectra is taken with a 785 nanometer laser, and the nanotubes are in air. And so you can see you have this nice spectra with a G peak right around 1590 wave numbers. And this peak, it corresponds to the vibration of the carbon atoms longitudinally along the length. Now, if you take you don't get a G peak. The reason for this is because the electrons that you're probing with that laser have been depleted by the acid and now are no longer available for excitation. However, if you use a higher energy laser, such as 514 nanometers, you probe higher energetic electronic transitions, and now you recover this G peak. And what's interesting is that the position of that G peak has shifted by 23 wave numbers. So we'll refer to the shift going forward as a DG. So this is an increase in G peak shift, which is a direct measure of the increase in the carbon-carbon bond stiffness, which is, again, a way for us to quantify the strength of the interaction between the acid solvent and the nanotube. So a stronger interaction will result in a higher shift. So we can do this experiment with some of the materials in our lab. So here I'm showing the G peaks for 4 different single-well carbon nanotube samples. And each of these materials in air has a G peak right around 1590. So you can see how their G peak shift to different extents. In this case, sorry, they're dissolved in oleum. And we can quantify those shifts. So if we go through this data, HIPCO, which has a diameter of about 1 nanometer, shifts in oleum by 28 wave numbers. CG301X, which is a smaller diameter nanotube of about 0.8 nanometers, shifts by 24 wave numbers. Then we can move on to EC1.5, which has a diameter of 1.5 nanometers, shifts the same as HIPCO, 28 wave numbers in oleum. And then when we move to the largest diameter sample, MEC 2.0, this material shifts by 37 wave numbers. So this is a massive increase in G peak position relative to the other 3 samples, which only shifted by 28 wave numbers. So to try to explain this, we hypothesize that perhaps these nanotubes are filling with the superacid. So if we compare the relative size of the nanotubes to the acid molecule, you can see in the case of the small diameter carbon nanotube, it seems unlikely that one acid molecule would very easily be able to fit inside. As we move to a large acid molecule could probably fit inside, but it doesn't seem plausible that 2 would be able to slide past each other. And in the case of the largest diameter tube, clearly 1 molecule would fit inside, and 2 could probably pretty easily move past each other. So we think this is the onset of the diameter required for nanotubes to fill with the superacid. In fact, if we look in the literature, we can find that graphene in chlorosulfonic acid has a shift of 33 wave numbers. And of course, graphene is being protonated by the top and bottom surfaces, increasing the G peak shift. So we think the reason that this material shifts by 37 wave numbers is because it's being protonated by the internal and external surfaces. So if we continue to examine this material, we can look at the phase behavior in chlorosulfonic acid and oleum. So you can see in transmitted light, the chlorosulfonic acid sample is a homogeneous color. However, in the oleum sample, there's a lot of structure in the fluid. Now, what's important to note in the oleum sample is that you don't see any black or opaque particles that would be undissolved nanotubes. In fact, the material has this nice brown color and everything seems relatively transparent. If you go to the cross-polarized light images, you see that that structure in the oleum sample is actually birefringent, indicating that you're actually looking at the liquid crystal domains. So what this tells us is that in the case of the oleum sample, both of these systems are biphasic, so there's coexistence of isotropic and nematic liquid crystal, but the concentration difference between the isotropic phase and the liquid crystal phase in the oleum sample is very high, so you can see the difference between the two spatially. Whereas in the corresponding acid sample, the concentration difference is similar. So based on this hypothesis, that the nanotubes are in fact filling with oleum, we can think about how we can take advantage of this by developing a new dissolution strategy. So we'll call this the oleum first strategy, where we take purified carbon nanotubes and we dissolve them into 0.5 milliliter, which is a small quantity of oleum. Then we take that sample and we dilute it with a non-corrosive acid. So this is 9.5 milliliters of methane sulfonic, phosphoric, and terephthalate sulfonic acid. And you can So that's promising already. So going forward, we'll denote these with a little shorthand. So we'll call methane sulfonic acid MSA, phosphoric PA, and paratoluene sulfonic PTOS. And we'll denote that it was dissolved by this oleum first strategy OF. And at this point, I need to note that PTOS is actually a solid at room temperature, but it melts very easily by heat gun at 40 degrees Celsius. So to investigate whether or not these nanotubes are actually thermodynamically dissolved, of course, we can look at the G peak shift of the DG, and then we can look at the samples under the microscope. And so I have them arranged from left to right with decreasing G peak shift. So phosphoric acid shifts by 32 wave numbers, methane sulfonic shifts by 30 wave numbers, and PTOS shifts by 26 wave numbers. So all of these G peak shifts should be sufficient for thermodynamic dissolution. Now, if you look under the graphical in the transmitted light images, you can see again there are no black particles. In fact, the nanotubes appear to have this nice pink hue to them. And again, structure which is reminiscent of what we saw with the oleum sample. So we know that this is actually the liquid crystalline phase that you're looking at. So this is really exciting. Clearly, we have nanotubes thermodynamically dissolved in non-corrosive acid solvents. So this should enable us to do some really interesting things. But before we look at that, the next question one might have is whether or not this oleum first dissolution strategy is actually necessary, or whether or not the nanotubes are indeed filled with oleum. So I'll remind you that the oleum first strategy is where we take nanotubes, dissolve them into a small quantity of oleum, and then dilute with new acids such as PTOS. Alternatively, you could take the nanotubes and directly add them to a mixture of PTOS and oleum, which is what we've done here. So we'll denote this as direct addition, or DA. So the two samples addition sample is black. So what this suggests is that there's a different amount of electron depletion between the two samples, but the strength of the interaction between the acid solvent and the nanotubes is different, which of course we can quantify with Raman spectroscopy. So the oleum first PTOS sample had a shift of 26 wave numbers, and we confirm that the direct addition has a lower shift of 19 wave numbers. So this is really interesting because what this tells us is that the order in which we add the nanotubes to the acids actually dictates the strength of the interaction between the acids and the solvent. So we can take this investigation a step further and precipitate the nanotubes from the acid solvents. So we wash it away with water until it's neutral. And then we take that sample, we freeze dry it, so we remove all the water. Now you have the solid nanotubes that have been recovered from the acid. We place them into a thermogravimetric analysis to see how the mass changes as we heat it up. And the oleum first sample decreases in mass by 19 weight percent. The direct addition sample decreases by a lower amount, 13 weight percent. Both samples have a large decrease around 400 Celsius, while the oleum first sample has a second decrease around 550 Celsius. So what this tells us is that the molecules that are desorbing in the oleum first sample at this high temperature are much more stable. This is what you would expect if the acid molecules were on the inside of the tube. You would expect that it would be much more difficult to remove those acids from inside the carbon nanotube than if it would take a higher temperature to pull them out. Similarly, we can perform Raman spectroscopy to see how much, to quantify the strength of the interaction of the residual acid in the sample with the nanotubes. So we see that once they're dried and we've washed away as much acid as we can, the oleum first sample still exhibits a shift of 20 wave numbers, whereas the direct addition has a lower shift of 7 wave numbers. So this data tells us that not only is there a higher amount of residual acid in the oleum first sample, but it's directly interacting with the nanotubes. So we think this data helps us confirm that the oleum first samples really does result in C1 carbonate tubes filled with oleum. So the next question you might have is, well, is this even useful? Well, the goal of all this is to allow us to process nanotubes in a thermodynamic solvent in ways that you could not do with superacids. One of these ways is actually Meyer rod coating onto plastic or transparent substrates. So in Meyer rod coating, we're going to take a nanotube solution and meter it out onto a flexible, transparent piece of plastic, and we'll spread that ink into a thin film with a wire-wound rod. Once you get the nice coating onto the plastic substrate, you can submerge that into a coagulant that washes away the acid and causes the nanotubes to precipitate onto the film, as you see here. So the gray in this image is the transparent film of nanotubes. Underneath it, I placed a piece of paper that has an out. That SEM image, you can see that the nanotubes are slightly aligned in the drawdown direction. So we can characterize the performance of this thin film by measuring the sheet resistance of a particular transparency. So this is a 90% transparent film, and we measure a sheet resistance of 60 ohm per square. So in this case, a lower sheet resistance is a higher performance thin film. And if you make a thin film like this with a direct addition sample, you get a sheet resistance of 130 ohm per square. So what this tells us is that not only is the oleum first result in a higher strength of interaction between the acid and the solvent, the solvent and the carbon nanotube, but that directly correlates to a higher performance in microscopic material. And we can compare how these thin films perform relative to what else is in the literature. So here we're plotting the sheet resistance versus transmission of thin films of the highest performing carbon nanotube materials in the literature. So these and superacid processing. And again, in this chart, lower sheet resistance is a higher performance thin film. You can see that we outperform aqueous and solid state, and we're on par with what you get with superacids. Additionally, I have here the values required, the benchmark values for liquid crystal display applications and touchscreen applications. And the red dashed line is the range of values that you get with indium tin oxide, which is the material that's in most cell phones and TVs. So not only do we meet these benchmarks, but we are on par in the literature. So we think that this emphatically does, yes, confirm that this is very useful. So not only are we able to thermodynamically dissolve nanotubes without sonication, without covalent functionalization into a solvent, and into a material-friendly solvent that allows us to coat directly onto fragile substrates such as PET, but we're getting electrical conductivity that's on par with what you get with superacid processing.
Is this resistivity
for the other line films at least, and we never tried, so you have to measure it in a larger area, and we never tried with these. So I don't know the answer to that. So we take this a step further to try to demonstrate the utility of these new acid solvent by benchtop silk screen printing. And in this case, the acid solvent does not damage the silk, doesn't damage the mask, and it doesn't damage the wood. We can also coat polyester fabric, rendering it electrically conductive. And in here, in this case, we have injected a porous carbon nanotube wire into a polycarbonate block that we're now using to light this LED. Now, one of the cool things about PTOS, as I said earlier, is that it solidifies at room temperature. So you can easily melt it with a heat gun, turn it back into moisture, which forms a monohydrate. The monohydrate has a melting point closer to 150 Celsius, causing it to solidify as it reacts with the water in the air. This allows you to directly extrude freestanding, self-supporting structures of the carbon nanotube solution. So this is essentially enabling us to 3D print carbon nanotube structures. And I'm doing this just on a piece of paper on the benchtop. So we've taken this all the way to modifying a commercially available low-spot 3D printer, where we've attached an extrusion pump. So we're able to 3D print carbon nanotube structures with this equipment. If you wash away the acid, you're left with a self-supported pure carbon nanotube structure, as you see by this SEM image. And so the dashed lines are showing the traces of the print head. You can see that the printed layers have merged together. And you can see by the white arrowheads that we're able to print sub-millimeter scale pores into the structure. If you cut open one of those printed layers with the focused ion beam, you see that the material is composed of thin sheets of nanotubes, making this a really porous carbon nanotube structure, which gives it a very high specific electrical conductivity for 44 centimeters per kilogram. So this is really exciting because this is the first time that anyone's ever been able to demonstrate 3D printing of pure carbon nanotube materials. So in conclusion, be filled with oleum and then dissolved into new non-corrosive acid solvents. And this mixture of oleum and PTOS, for example, is highly compatible with lots of different materials. We're able to get macroscopic electrical conductivity that's on par with what you get with superacid processing, and then the unique properties of PTOS actually enables us to 3D print pure carbon nanotube structures for the first time. So to conclude my talk, I'll just remind you that in the beginning we talked about how we can characterize structure property relations in carbon nanotube fibers by producing aligned films and transforming those into high-performance nanotube fibers. We developed a microscopic technique for measuring linear density of short carbon nanotube fibers, and then we demonstrated yielding high-performance macroscopic materials. So that is everything I have. I need to thank my advisor, Matteo Pasquale, my committee, Professor Kono and Professor Marti. Thank you for being here. Of all my collaborators, my funding, thank you to my CF2 lab mates, my friends, and my family. I'm very happy that I got to share this with you. I'm happy to answer any questions.
The thesis are open for discussion and questions.
Do you use CSA in the oleum first process instead of oleum, or is it just too reactive when you?
CSA doesn't play well with other acids. Just, I don't know. To be honest, I have no idea why, but it doesn't work.
In similar vein, I noticed all of your oleum first to use acids as a second solvent. Does it have to be an acid?
I don't know. I don't know. So it's a good question because even the phosphoric acid sample is actually 85% phosphoric acid and 15% water, and it's still resulting in the highest shift of 32 wave numbers. So probably not, as long as you can find something that doesn't necessarily react with the oleum and pull it out of the tube. But I'm not sure.
Sorry?
On the, can you go back one slide?
One slide.
We have a, yeah. Oh, yeah, that guy. I was just wondering, when you are flying it under tension, does that result in higher?
Increases in frequency.
Okay.
Other questions? So is there a relationship between linear density, tension, and resonant frequency derived in the limit where the string has bandmix difference or not? No bandmix difference. You know, maybe before always raised to elastic modulus, and I just don't know if it plays into there. No such assumption, that's fine. I mean, it could be a string that has no bending elasticity unless you tension. But you know, if you look at PTOS strings, it's almost true. Like floppy strings, it's almost true. So maybe that's the limit.
On the same vein, does this relationship account for, is it measuring the linear density of an untensioned and unelongated fiber, or is it measuring, along Mateo's question earlier in the talk, you're getting a bunch of linear densities as you go. Are those accounting for the change in the linear density? Because if you stretch a fiber with the linear density not going down, it just doesn't matter.
Sure, so
it's
the
well, yeah, and that trend actually is opposite of what you would expect, because the lower frequencies with the lower diameter rate to something else.
Other questions? Sorry, we're not